Hey everybody, this is slides 31 through 36 for section 3.2. We're just going to kind of clean up the last couple things here around solving systems of equations. So our last, we want to talk a little bit about what if there are fractions in them. If there are, the easiest thing to do is to multiply the equations by a whole number to get rid of the fractions. This is the same thing we've done before. The number you will multiply by will be the least common multiple. Let's do one. On your next slide, you'll see this system of equations. The second one has fractions in it. So to clear those fractions in this equation, we multiply both sides of the equation, right? We multiply everything in the equation by a number that will allow us to eliminate both a denominator of 4 and a denominator of 3. That'll be the least common multiple of 4 and 3, or least common denominator, which is 12, because 4 and 3 both go into 12. So if we look down here on the next line, you'll see that they're multiplying 12 through every part of the equation. So what you don't see here that you might wonder about is 12 times 1/4, right, is 12/4, which is 3. That's where the 3x comes from. If you do this, you can do the same problem by cross-canceling. 4 goes into 12 3 times, so you get 3. Those are the same thing. Okay? And then I'm going to erase those. The second one is 12 times 1/3, so that's 12 over 3, which is 4, and that's where this 4y comes from. 12 times 1 is still 12. So you'll notice we now have a new equation that has no fractions in it, but it's equivalent to the original equation. To finish this, you would solve this set of equations just like we did the other ones, elimination or substitution or graphing. And you'll see that equation E is the one we came up with when we got rid of the fractions. Okay, so let's do an example. It says get rid of the fractions, maybe we should say eliminate the fractions in the system of equations. Okay, so once again, this first equation I'm going to multiply by 12. And don't forget to multiply by 12 on both sides of the equation, right? On the left side and the right side. When I do that, I'm debating how much work to show here, but I think I'll show it all. 12 over 1 times 2x over 3 plus 12 over 1 times 3y over 4 equals 144, right? So the quickest way to do this is to cross cancel. 3 goes into 12 4 times, and 3 goes into 3 once. 4 goes into 12 3 times, and 4 goes into 4 once. If you don't get that, just multiply the whole thing out. Okay, so now we have 8x over 1 plus 3 times 3y is 9y over 1 equals 144. And the whole reason we did this was to get rid of the fractions. Right? So now, the first equation that we have here, we know is also equal to 8x plus 9y equals 144. I'm going to erase the work I just did so I can do the same thing with the second equation over here. Okay, so on the second equation, we see the denominators are 2, 3, and 18. So what number do 2, 3, and 18 all go into? Well, happily, there's a number, and it's 18, which makes this doable. 1/3 x plus 7/18 y equals 1/2 times, don't forget to multiply by 18 on the other side. Okay, so we have 18 times 1/3 x plus 18 times 7 over 18y equals half of 18 is 9. So 3 goes into 18 6 times. So I have 6x here plus 18 goes into 18 once. So I have plus 7y here equals 9. Now I have my second equation with no fractions in it. This would be easy to check and make sure I did this correctly. Well, I take back what I was going to say. So now here are my two new equations, no fractions, but equivalent to this guy over here. So now I would solve this in the usual manner with either, substitution, addition, or substitution, elimination, or graphing, okay? Next slide, two other special cases I want to talk about here. And these two special cases are when either you get an answer that looks like this. That tells us the system has an infinite number of solutions. And it also tells us that the graphs of the equations lie on top of one another. These equations will be dependent, and since there's a solution, they'll also be consistent. And the way that you write these solution sets is curly brackets, ordered pair x, y, such that, and then you write in this space one of the equations. We'll do this, okay? The other special case is if a contradiction is obtained, such as 0 equals 7, so something that can't be true, then we know the system has no solution. It's inconsistent, okay? And the solution would be the empty set. Okay, so here's an example. So we're going to solve this system of equations and see what we get. I am going to solve it by elimination, and I'm going to do that by multiplying this top equation right here by 2. So I am going to go ahead and solve this, and then the next thing you'll see is what I get for a solution. Okay, so I multiplied the top equation by 2. I got the green equation when I did that. The blue equation is the same as the original t equation. I solved them and look what happened. I got 0x plus 0y equals 0. In other words, 0 equals 0. Because this is always true, this tells me that these lines are, that I have infinite solutions here. Any infinite solution. So let's just think about this for a second. This problem is two equations that lie on a coordinate axis. And what we're trying to do is figure out when they intersect. Well, if you do the solution and it's always true, what do you think is true about those lines? So if I graph line R, I'll get something like the green line here. And then if I graph line T, I will get the same green line. And one way you can tell that this is going to happen ahead of time is that these two equations right here are multiples of one another. You see, 2 times negative 2 is negative 4. Negative 3 times negative 2 is positive 6. And 2 times negative 2 is negative 4. If they're multiples of each other, they're the same line. If you write them as y equals mx plus b, you get the exact same thing. Okay, so the way in which you write the solution for this is like this. X, y, an ordered pair such that. Now, it's not true that all ordered pairs are the solutions. What's true is that every ordered pair on this line is a solution, okay? So in order to indicate that the ordered pairs that lay on this line are the solution, in the solution set then you write the actual equation. And what this solution set says is For every ordered pair xy, any x and y that satisfy this equation are the solution set. Okay? The other thing you might want to write on here is that these are going to be the same line. And if you remember, we talked about consistent, which means there's a solution, and also dependent, because they're multiples of one another. This is the situation in which they're multiples of one another. Okay, last example here. So we're going to solve this system that consists of equation U and equation W. I'm going to use substitution for this because I see that A is already equal to something. Okay, so when I solve this, I substituted 4 minus 2b in for A because they're the same thing according to the first equation U right here. I solved it and I got 4 equals 6. Alright, well, 4 does not equal 6. So this tells us that there's no solution. And if you think about the situation in which there is no solution to two lines, it means the lines are parallel. Okay, and to answer this question, solve the system, you would just say there's no solution. Okay, that's your answer. Okay, those are the two special cases. That's it. Now you have some practice problems to do for these situations.